Hello and welcome to the first video of section 3 of this PyTorch Basics tutorial series. In this video, we're going to go through the start of our nonlinear neural networks by looking at activation functions, what they are and why we need them for our neural networks. So we're going to go through some basic examples and look at creating a nonlinear neural network by hand. And the data set that we're going to use is just this random one that I've created here. So we're going to do classification. So we're going to categorize our input data into one of two categories. So like previous sections, we're going to do binary classification. Except now, if you look at our data here, well, similarly to the other data, our data is not linearly separable. And what I mean by that is you can see that there's no way to really put a linear boundary between these two classes, right? There's no way to actually put a line anywhere that will perfectly separate these two groups or these two clusters. So if we're going to use a linear model, we won't get 100% accuracy. However, hopefully you can see those two groups still are pretty well separated, just not by a linear boundary. You can see if I put sort of a line here and a line here, we can kind of separate out the two groups, right? But a single line won't do that. And to see that that's the case, we can actually train using the same method in the previous section for our linear classifier with logistic regression. We can train a logistic regression model. So this is exactly the same as what we did in the previous section for the linear logistic regression. And we're just going to train basic model. And we can see that if we put our test data in, that decision boundary falls about here, right? And we have quite a few points not classified correctly. You can see we get an accuracy of about 91%. That's not too bad, but looking at this, surely we can do better, right? And before we actually go into training a model with PyTorch, what we're going to do is we're going to think about building up this a nonlinear model by hand. But before we do, let's talk about why we can't separate this linearly. Well, hopefully you can see that, as we talked in the previous videos, a linear boundary can only separate things that with a linear boundary. But why we need these activation functions in order to create our non-linear models? Well, if we go back to what we're really doing with a linear model, we're essentially taking our input data and multiplying it by a matrix or a matrice, and to get our output. If we just stack more of those linear layers after each other, right? Hopefully, if you remember back to your days of matrix multiplication, if I just stack multiple matrix multiplications, so if I've got my input X and I have some weight matrix W0, a bit bolder, and let's say this is a 1 by 2, this is say a 2 by 2, right? And then I get let's put another one, which is another 2 by 2. So put another one, this is a 2 by 1 to get my 1D output. Hopefully you remember that we can perform this sort of matrix multiplication in any order. So I can multiply these two together first, and I can get 0, 1, which is going to be a 2 by 2. And then I can sort of multiply these two together to get a 2 by 1. And then we can basically simplify this whole thing into just X, which is 1 by 2, multiplied by 2 by 1. So what this is telling us is that there exists some single 2 by 1 matrix that is the equivalent of multiplying by these three matrices, right? So stacking multiple linear layers is just the same as doing a single linear layer. We need some way of turning this into a non-linear model, right? So another way to put it, our linear layers, or our matrix multiplications, if you remember back to your matrices, what a matrix is doing to our input is either sort of rotating, scaling, or translating our input. But it does that to each point by the same amount, or linearly by the same amount. What we want, and what we'll see, is that we don't really want to treat each point in our space the same. What we'd like to do is we'd like to shift them, scale them, rotate them by different amounts, depending on where they are in the actual input space, or a hidden layer space that we'll see. So this addition of these non-linear activation functions and this idea of hidden layers, as we'll see, is what really defines a deep neural network, which really defines deep learning. It's this stacking of linear layers, or basic layers, with these activation functions that make our model a non-linear function approximator. Okay, so let's see how we can do this by hand. So let's go back to our ground truth data. What we're going to do first is we're going to assume that, or we're going to treat each of these input dimensions of our data, x0 and x1, we're going to think about them independently of each other. So we're going to assume that our input is one-dimensional for now, right? So you can see if I just look in the x0 direction, ignoring the x1 direction, we can put a decision boundary at about 1.5, and that will sort of separate out roughly this side, this cluster from this cluster. However, it won't do a good job, right, at separating out these values here, right? But for now, we're just going to put a decision boundary right about here at 1.5 x0. If you remember back to the previous section in the video for the linear logistic regression, I go through how we can do that. Right, I've got a bit of a summary here. We're just basically going to erase this, use that general form of the line equation, right? Right, we rearrange this, equals x, which in our case is going to be 1.5. And then we just pick some value of x1 or x0. We're going to pick some value of x1. We set it to 1 for now. We can calculate x0, or we're going to set x0 to 1 and calculate x1 from that. And you can do that pretty easily here. So that's for x0. And we're going to do the same, where are we, for x1. We're going to put a decision boundary at 1.5 again. So that's basically the exact same calculation. So we're going to get two one-dimensional inputs of two one-dimensional models, two one-dimensional linear models, and we're going to put our data through that. So we can stack those together in a 2x2 matrix. So we're going to get a 2x2 matrix. So here's my input x0, x1, my 2x2 matrix. So x1, we're going to have there. And for the weight for x1 for that first model, I'm just going to make it 0. So I'm going to ignore that other dimension for this first model. And I'm going to do basically the opposite for the x1 model. So hopefully you can see that what we've got here is just two independent one-dimensional models, and then I'm going to add my bias onto this. So that's a 1x2 by a 2x2, and we're going to add on a 1x2 of our x1, and that's like omega 1 or w1 and omega 1. It's going to be the same for both, and that should give us, let's call it y. We'll call it h actually. Hidden 1 and hidden 2. That will give us our 1x2 output. So what we've effectively got here is 2 outputs for every one 2D input. So we're going from a 2D space to another 2D space. Okay, we're going to ignore the sigmoid for now. And let's just look at what we've done. So this is our raw data here, right? It's our original raw training data. And this is our raw output. This is what we get after we put our data into, well, through those two, you could think of them as two independent 1D linear classifiers, or linear boundaries, sorry. You can see we haven't really changed the shape of our data at all, but what we've done is we've shifted, right? Hopefully you can see, look at these values, we've shifted the data down and across so that we've put that sort of gap between the two groups at 0 in both directions. Now, unfortunately, we still can't separate this out with a linear layer or with another linear model. What we're going to have to do is, or what we want to do is, we sort of want to stretch this data out, and we'd like to push these values around in an unequal way. Like I said, with a linear model, linear layer, it's going to treat every point sort of the same. It's not going to sort of unevenly shift these values around. And that's where our activation functions come in. You can see I've put the output of that first layer, right, H here. I've called it H1, so this should be really, well, this should really be, you know, H11 and H12. I put that through a sigmoid. At the moment, you can see it doesn't really change the shape that much. But if you remember back to our sigmoid function, right, it looks something like this. Hopefully, I can do a somewhat faithful, ooh, that's not very good, drawing of it. This goes to 0, and this is 1. It's about 0.5 at 0. Close to 0, the sigmoid function is very linear. It only starts to get nonlinear here and here, right? Once the values have increased, you know, a bit away from 0, right? So back up here, we picked a value for omega naught, W naught of 1. And you can see it has, as a result, we haven't really scaled the values of our data into that hidden layer, that hidden dimension, all that much. Now, if you remember back to the previous video in section 2 for the linear logistic regression, I said we can pick any value for this. And the only effect it's going to have, it's not going to change the location of this decision, you know, where we put this. All it's going to do is scale the values. And because it's a linear layer, it's going to scale the values equally, right? So if I say 5 instead of 1, you can see it's still centered at 0, but now we've, you know, multiplied the values and sort of stretched them out. And look at the effect it's had after we put it through the sigmoid. You can see we've now started to squish the values unequally. These values here up at 8, for example, well, they're pulled down to 1, right? And the values around 1 kind of stay where they are, right? Same with the negative values. Negative 8, that's now pushed up to near 0, and 0, of course, is pushed up to 0.5. But you can see it's treated the values unequally. The values around 1, around negative 1, have kind of, well, the values around 1 or 0.5, they've kind of stayed where they are. But the very large values have been squished a lot more. And you can see the sort of gap is starting to open up here. But we're going to have to increase omega naught a little bit more to actually increase that gap. So you can see now we're starting to get this gap here where maybe we can define a linear model to separate these two groups out. Let's increase it some more. There we go. So now hopefully you can see the raw output, the shape has not changed. It has scaled the values pretty obviously, but you know, it hasn't actually changed the shape. And you could do rotations and you could do a whole bunch of other things. Right, you could rotate this, you could sort of skew it a bit, but it's not going to allow us to linearly separate the data. However, after this sigmoid function, we've squished these values right up against 0 and 1, and has opened up that gap quite a lot, such that we can now create, if we just define another layer that takes in the output of the sigmoid after the first two, or the first one 2D linear layer, after the sigmoid, if we can now define another linear layer that takes that as an input, we should, with 100% accuracy, separate out these two groups. So let's do that here. All we're going to do is we're going to pick 2 points. I've picked 0, 0.6, and 0.60, or the other way around, these 2 points here, and I can just fit a line very easily, just draw a line between these 2 points. Hopefully you know how to do that. It's not too difficult. I've got 2 points, and I can sort of define a line using that. Again, you can pick any value you want for omega 0, omega 1. This is now a 2D line, so we're going to use this form of the general line equation. So that should be x1. You can pick any value you want for omega 2, or you can pick the other values of omega 1 and omega 0 first, as long as you plug in your values of, where is it, 0.60 and 0.6. You say that those 2 points should lie on this line, so that should equal 0. You can solve for that in any way you want. And the line I've created is just 1, 1 for omega 0 and omega 1, because it's really just a 45-degree angle line. And then we've just set our bias up by 0.6, right? So that the intercept is at 0.6. Okay. So we're going to take as input to this linear layer, H2, which is hidden layer, after the sigmoid. And we're going to then classify with our decision boundary at 0. So we've got this line here, and we're going to set the boundary at 0 distance, threshold at 0. And I'm going to calculate the accuracy after that. So this will turn it into 0 and 1. And you can see we've got a 100% accuracy. So that decision boundary there perfectly separates out these two groups. So there we go. We've now created a very simple non-linear model that's able to separate out this more complicated data that a linear model can't. So hopefully you can see with this very simple toy example why we need non-linear models, right? And how we can build up a non-linear model with many linear models, right? And this idea of this hidden layer, which is basically the junction between two linear layers that we usually put a non-linear activation function to unequally stretch and warp that space. Another way we think about what we're doing here is by mapping the input space into a new space, which is what we're showing here. This raw data, that's our input space, and we've mapped it to this H1 space. I'm calling raw output, it's H1, with a linear model. That linear model is going to maybe stretch a little bit, rotate, scale, but it's going to do it in a linear way, right? So you can imagine we sort of stretch this out in different directions, but it's not going to unequally stretch them out. We need to then map it again to a new space with some non-linear function, such as a sigmoid function. And that new space, we want that new space to now be linearly separable, right? So what we need to do is we need to adjust the parameters of the first linear layer such that once it's squished by this function, which is a fixed activation function, once it's passed through that, it now becomes linearly separable. And that's the whole idea behind deep learning, right? In fact, with a single hidden layer with a nonlinear activation function, we can theoretically approximate any function, so long as the hidden layer is infinitely large. So basically, with enough dimensions in this hidden layer, here we've only got 2, but we're not limited by 2. I've just got 2 here because that's all we need, and it's easy to visualize, but we can have as many as we want, right? And with enough, we can approximate any function. However, as we'll see in deep learning, we tend to add more layers rather than wider layers because we get a bit more of a better generalization, and we'll talk about that later. Okay, so hopefully you got some idea now how our nonlinear activation functions work and what they do. So we can actually visualize the predictions for our training data. You can see we get that perfect separation. So we're using our class predictions here, not the ground truth. So we are getting this perfect separation with our nonlinear model we've defined by hand. Okay, so now that we've seen why we need activation functions and what they're for, let's see how we can create one with PyTorch and train it. So the basic training is exactly the same as our linear logistic regression, except now we're going to define a nonlinear model with a single hidden layer with our sigmoid there as well. So we're going to use our nn.module class constructor to build this network from two separate linear layers. So a bit more complicated now. So all we need to do is define as a class variable each of our linear layers. We've got input size, hidden size as the output for the first layer, and our second layer, of course, needs to have the input size be the same as the output of the previous layer, which is our hidden size, and then the output of linear 2 will be our output size, which will be 1 in our case. So input will be 1, input will be 2, hidden will be 2, and output will be 1. If you remember, our forward pass defines the actual equation of our model, right? Defining the layers here just defines the actual layers, doesn't tell PyTorch what the actual architecture is, it just tells it what building blocks we have. So we need to define the actual forward pass here. So we take X, which is our input data, pass it through our first linear layer. I'm just going to set those to a class variable so we can look at them later on. But we take the output of that first linear layer, pass it through our nonlinear sigmoid function, get our H2 hidden layer, and pass that to our second linear layer, get our output H3, and return that as the output of our forward function. All we need to do now is define our model with our class constructor, input size 2, output 1, hidden size 2. We're going to use the same BCE with logits loss. We're going to use a different optimizer here. We're going to use the atom optimizer. Again, it's very similar to stochastic gradient descent, and we'll go into more detail on that later on. It just converges a bit better for this problem. Okay. So you can see we're going to be training for quite some time. Not really, compared to other deep learning problems and architectures, but you'll see that it does take a little bit of time to actually learn this model. So I'm just going to pause the video for now, and I'll get back when it's done. Okay, so we've just finished, and you can see our model, this should be our nonlinear model. It's got a 100% accuracy. Okay, so we can look at the training accuracy over time, over the iterations, and our loss as well. You can see, interestingly here, our model seems to converge at about 91% accuracy before it sort of goes up to 100% accuracy. You can see we've got this double sort of descent of our loss here. I think the reason for this is that, with this optimization, the model tries to fit the simplest thing possible. And the simplest thing to get a very high accuracy or low loss is to basically just have this linear decision boundary here. And it takes some time. As you can remember back here, we had to scale up omega naught to quite a large value, right? We had to scale the parameters of that first layer to quite a large value in order to get this separation here, right? And so that's what we're seeing here, right? We fit this linear model very quickly, but we have to scale, now that we've sort of rotated it in place, we have to scale those values so that the sigmoid function gets into its nonlinear region, and sort of those side branches here, that decision boundary sort of bends around, and we have to wait until the output or the parameters at first layer scale large enough. And so that's what we're seeing here. We sort of converge a little bit, and then the values start increasing far enough until we hit that nonlinear region of the sigmoid, and we start to decrease again until we get our 100% accuracy. So we can look at our predictions from our nonlinear logistic prediction. And we can see that we have, yes, perfect prediction. Another thing we can look at is actually that hidden layer, the output of the sigmoid. You can see it looks a bit different to what we got. What it's learnt here in this case, it's different every time, is it sort of reflected the values of the input first. If we look at the actual parameters of the first layer, yeah, you can see one of them is positive and large, and the other one is negative and large. You can see these values are quite a bit smaller. So it's actually reflected the values, or really one of these decision boundaries is sort of flipped the other way around, so that this is negative and this is positive rather than positive, positive, like in our model. You can sort of simulate that by making one of these values negative. Yep. And this one needs to be positive, not negative as well. So there you go. If you flip one of them, you'll get the same sort of boundary there. We'll also need to obviously change the second, the decision of the second boundary. So it'll be like, maybe you can do 0.6 there, but then it'll be, what's that, 0.61 here instead. So I'm just gonna wing it. It's one of these two that needs to be flipped. Yeah, you probably need to actually check what you're doing there instead of just randomly selecting. Hopefully you get the point, right? All it's done is flipped it. Again, it's still linearly separable. If we look at the parameters of the second layer, you can see one of them is now just negative. Yeah. Again, it's scaled. So we can look at the bias too. The bias will probably be quite large. It wasn't too large for ours. That's all that's going on there. So it's essentially pretty much the same thing. It's a bit random how it's going to actually, generate that decision boundary so that it's linearly separable for the second layer. But the point is that it needs this nonlinear activation function in order to do it, right? So one of the reasons we say that it's kind of hard to interpret what our models are doing is that, there's potentially many solutions and it's picked one of them, right? That might be a bit hard to interpret what it's actually doing. But in any case, what we do know is that it's obviously found some intermediate representation that is linearly separable, right? Thanks to the nonlinear activation functions. Okay, so that's just a very basic example of how we can create a nonlinear model to solve a problem that has a nonlinear decision boundary, or that requires a nonlinear decision boundary. And why is it important? Well, many real-world problems require the use of a non-linear model. In fact, it is pretty rare that we're ever going to get a really good performance out of a linear model. You can, in some instances, just use a linear model and it might be good enough and simple enough. Though these days, with the rise of deep learning, it's really easy to now implement a complicated non-linear model and get a much better performance. Okay, so that's all I wanted to say in this video. Hopefully you'll join me for the next video where we go into some actual implementations of some interesting non-linear neural networks to solve some more interesting problems. Thank you.